G'day everybody, hope everyone's well. So this is going to be the first video that I'm going to produce from my laptop. I'm currently just off the coast of WA near Exmouth, just here on the map. I don't actually have a whole lot of footage to play with. I didn't have anything in mind when I came up here as to what sort of video I could make. But I've got a few ideas down the track of some things I want to play around with on the Patrol engine. The reason I want to do this is because now that I have the BMW, I'm going to fix that one up and use that one as a daily driver, hopefully. Probably a bad idea using a BMW as a daily, but it's what I've got to work with. So, the topic that we're going to be delving into in this video, I'm going to be doing a bit of background research, is diesel water methanol injection. So this is a bit of a broad topic, but we're going to narrow it down and sort of explain the basics, explain the concept, and explain how the systems work and how you could potentially simplify and create your own system with basic parts, which is what I'm planning to do. Now, I can hear everyone already saying, why would you fit a water methanol injection to an RD28? They're painfully slow, they're painfully underpowered, and you're pretty much wasting your money. Well, I'll explain that. For those of you that don't know much about the RD28, it's actually quite a good engine on design. Certain choices aren't that smart, but if you compare it to something like a TD42, it does have quite a few benefits. So the biggest one, comparing it to a TD, is the fact that it has a forged crank from the factory. So TD42 cranks are notoriously weak because they are cast. If you make anything over 600 Newton meters, it's probably going to snap and you're gonna have a very, very bad day and a very, very empty wallet for a while. The reason the RD28 has a forged crank is because it's from the same engine family as the RB series, and don't really need to talk about the RB much, everybody knows it. Forged crank is a good benefit. It's very strong and it allows you to create a lot of power and a lot of torque without having to worry about potentially damaging the crank itself. The rods and the pistons are also quite strong. There's people that have made 50 psi of boost and the engine's happily had it for a while. The big killer with RD28s is improper or incorrect injector timing. This can cause extreme pressure spikes when you don't want it, and this will shock load the pistons and the rods and just do a lot of damage if you're not sure what you're doing. So with that out of the way, we'll start talking about water methanol injection. So to anyone that has not heard of this concept before, you might be thinking, why the hell would you inject water into an engine? Doesn't water hydrolock an engine? Yes, water can hydrolock an engine. If you're not sure what a hydrolock is, that's when enough water finds its way into the intake system and into the combustion chamber that when the piston comes up, the volume of water is greater than the volume of the combustion chamber when the piston is at top dead center. This will cause the piston to react against this almost incompressible medium, and this will bend the rod, try and stop the piston dead in its tracks, and just cause a whole lot of dramas and pretty much destroy an engine. Now, if you're able to controllably inject or controllably mist water or methanol into the intake of an engine, what this does is it cools the intake temperatures down drastically. So I'm sure most of you have seen the Mighty Car Mods video about cold air intakes, and in that video on a turbo car it shows that there's nearly no, in fact there is no benefit to having one. All it does is cool down your air intake. Now that is on a petrol engine. Petrol engines benefit greatly from cold air intakes as cold air going into the engine is more dense with oxygen, and as well as that, colder intakes and mean colder combustion temps, which lower the chance of knock, which is the absolute killer with petrol engines. This allows you to add more timing and create more power. Diesel engines are quite different. With a diesel engine, you're not worrying about timing because the pump's doing all of that by itself. All you're worrying about is the amount of fuel going into the engine and the exhaust temp that's coming out of the engine. Now what you're needing to consider is that diesel engines have a much higher compression ratio than a petrol engine, and so it may actually not be favourable to use methanol in your system. Methanol is an alcohol-based fuel and it burns a bit slower, or quite a bit slower than petrol, and it also doesn't burn as hot, which is why it's favourable to use in race car engines, as well as that it has a much higher octane rating. This is a problem if you're using it in a diesel engine. This is because the diesel engine may create such high compression temperatures that it'll ignite and knock the actual methanol itself. So in this case, it is actually favourable sometimes to not run any methanol with diesel injection systems and just run straight distilled water, which is what we're planning on doing. Water itself draws more heat out of the intake than methanol will, but the only downside to water is that it has a lower freezing point. So if you want to run one of these systems if you're in a cold climate, you'll have to keep that in mind, as it could be potentially catastrophic to your setup. So as the water evaporates, what it does is it draws heat out of the surrounding atmosphere. This is because all of the water atoms that are running around so close to each other, as soon as they expand out, they absorb the energy from the surrounding atmosphere to heat back up to a normal critical temperature. If you've ever jumped out of a pool and a gust of wind's blown past you, the reason you feel so cold is because the wind is evaporating amounts of the water off your skin, which is drawing all the heat out of your skin and dissipating it into the atmosphere. So colder air intakes on a diesel engine mean that you'll be able to cool down your combustion temperatures and in turn cool down your exhaust gas temperatures, meaning that you'll be able to add more fuel and create more power just by squirting a bit of water into the intake and not worrying too much. The other end benefit that a water methanol injection system will have on a diesel engine, like mine, that's old, full of carbon and just absolutely disgusting, is that it will clean out the combustion chambers and the intake manifold. So I'm sure you've all seen videos of people using sea foam on engines. This is just some kind of water-based substance that's squirted into the intake while the engine's running. This can break up the carbon deposits on the combustion chamber and just clean up the engine and make it run a bit better. So as the name suggests, water methanol injection injects water and methanol into your engine. So any system that injects something is going to need a pressure source. Pressure is created via a pump. There are many different kinds of pumps, which we'll talk about, but in the essence of a water methanol injection, you're going to want a pump that can supply a constant pressure. So this rules out any reciprocating pumps, like a piston pump. So we're going to probably go with a rotary pump because that's what normal manufacturers use. Things like AEM and any off-the-shelf water injection system, they utilize a pump, most likely a rotary pump, same premise as your fuel pump, but slightly different components so that it isn't rusted when you put water through it. So if you look at the pump that AEM uses on their system, this pump is rated for 200 psi of pressure. So the maximum output pressure of the pump is really based on what kind of injector you're running. So if we look back to a diesel injector system, the injector pump has to create upwards of 1000 psi because the cracking pressure on the mechanical injectors on a diesel injection system requires said amount of pressure for them to function and actuate properly. Water methanol injection systems share more similarities with the injection system that petrol engines use. They use a much lower system pressure because the injectors are opened by an electronic source. So these injectors act as solenoids, not requiring any said pressure for them to function. They simply open when signal is given, allowing said pressure to go through them and be injected into the receiver. Now where things start to get a bit more complicated is when we talk about atomization. So atomization is the ability for any injector to properly mist the injected substance. So if you think to any cafe that has water misters around to keep people cool, the nozzles on these systems create a very fine mist because the output water is sprayed out in a very large wide pattern, and this in turn means much smaller groups of water molecules, making the evaporative cooling much faster than if there were big globs of water coming out. So the essence of that is that a higher injection pressure can mean a much better atomization, but the atomization is much more dependent on the type of injector that you run. Diesel injectors have a much higher pressure. This is because, for one, they have to inject into a high pressure environment, and the pressures fighting against each other means that the injector pressure has to be much higher to counter the back pressure inside the combustion chamber. But in the essence of a water methanol injection system, depending on where you put your injector, so the options you have are to inject the water pre-turbo, inject the water post-turbo, or inject the water as soon as you can before it goes into the intake. All of these have reasons as to why you'd choose them, but in the case that we're doing, I would suggest injecting the water pre-turbo. So one of the big reasons for this is that you're not fighting pressure differential when you're doing this. So if you have an injector in your intake system, you'll be pushing against the 20 or 30 psi of boost with the water that you're spraying in. So this in turn does create certain problems. Depending on your injector geometry, it might actually hold your injector shut, but injecting water post-turbo can mean the water is slightly cooler when it's in the intake system because it doesn't get heated up by the turbocharger itself. However, if you inject it pre-turbo, what the turbo does is it helps atomize the water molecules properly so that they're able to evaporate faster. It will also assist in cooling down your pre-turbo intake, your turbocharger itself, but probably not much considering that thing's getting driven by 600-degree exhaust gas. And then the atomized water will hopefully cool everything down and cool down the intercooler itself, which will itself provide a cooling coefficient to the air going through it. So the lower pressure injection that we're going to be running from our water system isn't going to atomize the water properly. So if you can see these two photos here, you've got the comparison of a low pressure system and a high pressure system. High pressure has a much better atomization effect. However, the high pressure system needs above 250 psi to actuate the injectors properly because of their internal geometry. And so because of this, we're not able, or I haven't been able at the moment, to find a 12 volt pump that is able to generate above 200 psi of pressure. And so because of this, we're going to have to run a low pressure injectors and misters, which are not going to have as good atomization, but we'll be able to get by that by injecting it pre-turbo. So the actual misters that I'm going to be running, the company brand I'm looking at the moment is Holman. So they offer a system for water misting that plugs straight into a normal water tap. So standard water pressure, or the water pressure around Perth at least, is around 45 to 50 psi, so about 3 bar. This is low pressure, and so hopefully with that little bit of extra pressure that the pump's going to supply, about 120 psi, we're going to see a pretty good water atomization effect. And if we don't see that, we can probably modify the nozzle slightly and machine one or close up the orifice diameter so that it's able to supply less flow. What I'm aiming for is controllability of the water. Okay, so here's a drawn up PID diagram, standing for piping and instrumentation diagram, of the water setup that I'm going to be running. So it might look a little complicated, but I'll talk everyone through it and explain why this is the system I'm going to use. So we'll start at the water tank and the water pump. So it's going to need a water tank, I'm guessing around 5 litres of volume, but that's going to be determined by how fast we use the water once the whole system's running. So the water tank has water drawn out of it by the water pump. Now after the water pump, I'm going to put a pressure regulator in. So the reason for this is the water pump itself that I'm running, one off eBay, it's got an auto cut in and cut out feature to maintain 120 psi of pressure. So this is good but also bad for our system, because that's going to mean it might cut in and cut out and cause interrupted flow through our injectors. I'm going to put in a pressure regulator that's set to relieve just slightly under the automatic cut in and cut out. So this means that once the pump comes on, it's going to build pressure in the lines, and then it's going to maintain and hold that pressure because the auto cutout feature isn't going to be kicking in, and it's just going to be returning to the tank like in a petrol. So we'll go along and we'll go to the solenoid valves. So these two solenoids are going to be 12 volt driven, and they're going to allow me to precisely set them to open at certain times. These are going to be installed just before the water injectors, and the water injectors here, they're going to be installed pre-turbo, so just before where the turbo is in the intake. So onto the electric side of things. So the pump's going to have a relay, since it can draw a lot more current than the normal wire that the push button's going to run is. So you can see the relay here. We're going to have a push button in the cabin, a latching one, meaning you press it and it'll stay on, and if you press it again it'll turn off.
So this push button is going to pilot the relay for the pump, and that's going to turn the pump on with a wire straight from the battery. This push button is also going to go on and turn on these two wires which run through pressure switches. So these two pressure switches are going to be connected to the boost pipe. One's going to cut in at 5 psi, one's going to cut in at 15 psi. So this means one injector will come on at 5 psi of pressure of boost, and if I start to make more boost, then the other one's going to come on to cool down the excess of fuel as you get into higher boost due to the way my pump's set. And as well as this, I'm probably going to run two little 12 volt lamps. These are going to tell me whether the injector's solenoids are open, and this will in turn give me a visible indication if there's anything wrong with the system, if something shorts out, something earths out, and tell me if one of the injectors is stuck open, which would not be nice. So that's a brief overview of the system that we're going to run. A lot of talking in this video, so apologies if you wanted to see more hands-on stuff, but I don't have footage at the moment. And so this is the system I'll run. I'm going to put this together when I'm back in Perth, hopefully flying back on the 23rd. And if anyone has any questions, feel free to leave a comment, like the video, subscribe, and yeah, hope everyone's well, and I'll see you all in the next video.